So last week we saw a bit about the basics of objects in MATLAB, and we saw how to import NMR data. After the tutorial, I made this, I commented the code a lot. So everything I explain, in principle, you can follow it in the code. So when I explain a bit the difficulties that you can encounter, so all these green parts are comments that explain you what I'm doing. In principle, it should help you a lot. And I've put the data online. So if you open the code, you even have at the relevant places, you have the links to download the data and all that. This week, we will see how we can use a very useful tool of MATLAB, which is this curve fitting tool that is very useful for example, deconvolution, and in NMR in particular, the relaxation measurements. And I will start by saying that when you install MATLAB, this tool is not by default installed. So you have to be careful to install it when you install MATLAB, and you can always go back to it. It's just a module to add. I think if you use MATLAB for NMR, this tool is really super useful. I guess if you haven't done it, it should be using these buttons that you can install it. So I'm going to start with the same data that I've shown last week, which are hyperpolarized signal obtained in a dissolution DNP experiment in the liquid state. And here I've summarized just the code that I will use to start with. So I will run the whole code and then remind you what it does. So now everything applied. So first, this here clears everything I had in the workspace to start with something clean. Here I define the path where my data are stored. Here I import them using this function RBNMR. Then I keep only the first proc. The first proc is kept in position 1. So this is really a topspin way to define things. Here I store the data in a matrix. Then I created this function, this little bit of code that allows me to integrate or to select a region. So I have the full spectrum. The full spectrum is here, and here is the region that I selected for for integration. And finally, here's a region I selected for noise in case I want to do some to measure the error on the integral. Then I showed you how to remove empty spectra in the end. I'm not coming back to this. And
Quentin,
yes,
I have a question already. Actually,
mm-hmm.
You were just showing us some spectra. Could you bring those up again, please?
So, and by the way, to do this, I went in. I click here. So now I'm in this bit of code, and to run only this code, I click on Control, Enter, and then I run this section. Here they are. Yeah.
Wonderful. So I noticed that the axes are kind of the wrong way around for
yes.
what would be a chemical shift scale.
You say that this should be the opposite side?
Well, yes. So basically, it shouldn't be negative, but the scale should run backwards.
Yeah.
So I just wonder if you have something to sort that out. And also, just as a recommendation, I wouldn't put frequency and then have units of ppm. It should be chemical shift or hertz.
Yeah. Okay, I see. Mm-hmm. I agree. Reverse axis. I always forget how to write this, so I always have to go back. It's quite simple. So here's the command. In this case, I did not do it because I wanted to have the both. Oh, there's a mistake. Oh, sorry. What does it tell me? I should do it. That's what I wanted to do. I don't know why it's not happy. Usually this works. Oh, there's a capital letter here. That's wrong. I didn't want to do the reverse here
Yeah,
because
that looks nice.
I wanted to have them in the same order as here. But if you want to do
That's all fine. I just wanted to see how easy it was to swap it around.
These sort of things you ask Google and you find immediately. For example, if you want, sometimes it gets complicated when you want to do a plot with a logarithmic scale and have error bars and like you add many options together. Sometimes you have to seek a little bit how you can combine the options. But this one is quite simple because you use set. So you use plot, and after you've done the plot, you can reverse it. So it's quite simple to use. So this was to remove the empty spectra. And now this bit is the one, I'm going to run it again, that does the integration. So how does it proceed? I had defined earlier this region where I integrate. SB being signal boundaries, and when I plot it in the second plot of my graph, I plot from SB1 to SB2. So this is the x-axis, y-axis, and I go from SB1 to SB2, from this point to this point, and I get this region. So here, what it does is it sums the points only on this region. So I'm summing only this quadruplet, and I store it in I. So as you may remember, we have to be careful here. This number 1 means the dimension along which I sum the spectra. So you just have to be careful. Here you sum over the first dimension. The first dimension is the rows, and you sum all the rows together. And then I divide by the maximum. This is the way to normalize and to express my data from 0 to 1. And finally, I do a figure. And as a reminder here, I had also done something. I had took the D1 from the acquisition parameter and created a time axis, because this is not done with a VD list. If you have a VD list, you can also import it, creating a bit of code. In this case, it's a constant spacing between the delay between the spectra. So I import it here and create a time axis. So I have this variable t and I that contain my data, the time and the integral as a function of time. So now we're going to open this tool and see how we can perform a fit. This is a tool that we can use interactively, and then we will create a code that uses this tool. So first, I enter here my x data. X data is time, and y is integral, I. I'm gonna disable auto fit. This makes MATLAB fit every time you do a modification. I want to fit only when I click fit. So by default, it gives you some random function, but here what we want to use is a custom function, and I'm gonna write the function that we want. So in this case, I expect by theory, I expect the decay to be mono-exponential. So the way I write it, I will just fit the T1. And here I might modify because I want a function of T. Here I'm just gonna write I so that it's clearer for me. So now this, I'm telling MATLAB to fit this function. T is the x-axis, but T1 will be a free parameter that MATLAB will fit. I click fit, and it sort of works. And here I have a set of options. For now, we don't really need them. We will see at some point that they will start to be useful. In particular, we can give a starting point for the free parameter and define a lower and upper boundary. So for example, here, I might say that, of course, the T1 cannot be negative. And I can say that it shouldn't be more than 1,000 1,000 seconds, and it will start at 50 seconds, for example. If I run again, of course, I get the same results. Here you see the results of the fit. So this is the model that I'm fitting. And this is the results of the fit of the 3-parameter T1. And this is the interval of confidence with 95% bounds, confidence bounds. Here, the precision of the fit. So this is already we are done basically with this fit. So for example, I can what I can do now is to give it a name. Exponential fit. I've now extracted the T1. You can save a session like this. I'm going to save it in my tutorial folder. Yeah. Do you have any question on this? Okay. So now we are lucky that the quality of the fit is good enough for the fit to go through 1. It's not always the case. Sometimes we have too much noise, and we cannot just rely on this first point to define. I've really forced this point to be exactly 1. So what I can do is I've added this parameter I0, which is the intensity at time 0, and I can give it some. I say that it should be larger than 0 and maximum 2 and start at 1. I do the fit again, and I see that I can improve slightly. You may notice that there's some discrepancy between the model and the fit, and especially in the beginning here. The first points are not really aligned. This is due probably because to the instability of the spectrometer after injection of a solution. So in this case, you see it changes slightly the value of T1. We had something like 90 before, now we have 87. You can also duplicate your fits. In fact, it's quite interesting to do it like this. So I'm going to call this one fixed I0. This is the fixed I0. And this is free I0. It's always interesting to compare these sort of things. Now what we can also do, although it's clearly not justified in this case, I'm gonna do it just to show you how it works. You can also very easily create a bi-exponential fit. Exponential fit. So a typical way to write a bi-exponential fit would be this. I'm going to put it T1A. Oops. I'm going to give some constraints on my initial parameters. When you do a bi-exponential fit, you usually restrain this parameter A that splits between these two exponential. You force it to be below between 0 and 1. So in this case, the bi-exponential fit doesn't really work because this curve is really mono-exponential in nature, but this would be the way this would be the appropriate syntax.
Quentin?
Yes.
Is it possible to have 2 different fits on the same curve to compare the 2 of them instead of having 2 different sheets?
Not to my knowledge. I don't think it's possible.
Okay.
I will clearly do these sort of things, but I have to code it myself. On the fitting tool, you don't have. I don't think you can do that.
Thank you.
It reminds me that there are some interesting features also. I'm going to open right at this one. So exclude outliers. Yes. So for example, I might exclude outliers here. So saying, okay, these 2 points in the beginning, I don't want to include them in the fit. Quite interesting. And another one that is useful, residual plots. So this tells you the deviation of the model. So the line here is the model, and these are the experimental data, and you have the difference between them. So it's useful. Here you see that you really have a trend. In the ideal case, you have something like this where the experimental data are just some noise around the model. So here we see that we have a real problem. So this is enough to do a simple non-exponential fit. Now what I would like to show you is how I can do more complicated. Before I'm going to save this, so that you can have a look at it. Opening MATLAB.
May I interject with a strange question?
Yes, please.
For example, if you do the bi-exponential fit again.
Oh, sorry, I closed it too fast.
Or if you have some sort of function where you need to constrain parameters like a and b. So instead of having a bi-exponential fit where you have a and 1 minus a as the coefficient, you could have a and b, but you can constrain the sum of a and b to equal 1, for example. Is that sort of thing possible?
You can only write parameters here and define the boundaries here.
So there would be no way if you use a and b rather than a and 1 minus a to tell MATLAB that you want a and b to equal 1.
This, and now add a condition a plus b equals 1.
Yes.
I don't think this is possible. Usually you have to really rephrase your mathematical problem in a way that, I mean, that's the only way I know how to do it. So I agree. It's a sort of limitation.
Okay, interesting.
I think it makes a big difference in the way you can the algorithms you can use to do your fit. That's why.
Yeah. So just as an FYI, in Mathematica, it's possible to do such things.
Mm-hmm. Yeah, but it really modifies the type of fit you can do. Like here we were using. There are like some algorithms that they use. Anyway, interesting question. Now we are going to do something slightly more complicated. It's Lorentzian deconvolution. So first, let's plot a single spectrum. So I have my data here. I'm going to plot. Maybe I'm going to copy this and text. It would be easier. So what I'm plotting here is the first spectrum. I don't really want to do my Lorentzian deconvolution on this one because it has some weird shapes here. So I prefer to use not the first spectrum of the decay, but the second one, for example, which is slightly cleaner. I might show you the spectrum also like this, maybe easier. So now I ask MATLAB to do a plot where I use a cross for each point. So you see all the data points I have. And now I want to fit an analytical function to this data. So for this, I need to create two variables that I can open in the curve fitting tool. And so this here, what I'm creating is this will be a variable containing the x-axis and a variable containing the y-axis that I want to use in the curve fitting tool. I run the code so that now they are stored, the two variables I wanted to create. And I open the curve fitting tool again. I load as the x-axis the frequency vector. Same thing for the y-axis. It's now imported here. Now it will be slightly more complicated to fit this. Let's have a look at the functions I want to fit. So this is the expression for a Lorentzian with the width, the full width at half maximum, the central frequency, and the intensity at the initial intensity, the overall intensity. And if you use this normalization constant divided by pi, it means that this is exactly equal to the integral of the signal. So I'm going to use this function in MATLAB. I'm going to first start with a single Lorentzian, and so fit only one of the peaks and then the other ones. So I choose a custom equation. I0 divided by pi, as I said. And now it's the full, let's call it G, the full width at half maximum, divided by 2, divided by G divided by 2, and this is square, plus W0 minus W. I call it W, it could be, I mean, it's as a Stuart pointed out, it's ppm though. So it tells me that there's a problem here. What is the problem? Why isn't it happy? Expression I0 is not a valid MATLAB expression, has a non-scalar coefficient.
I think you may be missing the final bracket.
Oh yeah, all right, thank you very much. If I try to fit this, this will never work. I just know it from habit. I have to, there are too many free parameters here, so MATLAB is unable to handle it. First, you see that I0 will have an enormous value, and you see the starting point, the initial one, they are very small. So there's no way it can handle it without a bit of help. So first, I know that the initial intensity will not be negative. I know that it will be very large, in the order of 10 to the 9. Then G, the width, I can have a look here so this is more or less. Maybe I can. It will be clearer if I do it here. So I'm going to plot this again because I want to know more or less the width at half maximum. The way I do it, I zoom, so I have my peak here. So the middle is approximately here. So if I go from 180.3 to 180.32, it's approximately 0.02. So this will be my starting point for the full width at half maximum, 0.025 more or less. From 0, I'm constraining it a little bit more. And I'm first gonna fit one of the Lorentzians. So it should be centered at around 180.3. Of course, this will not work well. It has fitted this Lorentzian, but the fit doesn't work well because I have a quadruplet and I fit it with a single Lorentzian. But still, you see, it's not too bad. It's in fact surprisingly good. Now, what I want to do is to add the other part of the spectrum. I'm going to go step by step. So now what I add is J. J divided by 2. So plus J divided by 2 for one Lorentzian and minus J divided by 2 for the other one. And now I want to center, so the center is here, and have plus j divided by 2 and minus j divided by 2. I open this again to get the value of j approximately. So from 100, it's as you see, it's more or less 0.3 from one peak to another one. So this will be my starting point for j. I give it some more constraints. And now I want the center to be here, so around, let's say, 0.4. And as a minimum, I will constrain it a little bit more. Yeah, if I run the fit now. It makes the Lorentzian too large because it wants to include these in the fit, of course. So now what I have to add is to make it clearer, make like this. So now I have to add the same thing. Now I'm including these two as well. But you see, all these I have the same integral, which is of course wrong. This is larger than this one, and if you remember from like elementary NMR, using the Pascal triangle, you have this 1, 3, 3, 1 pattern that I can write this way. So it's 3, and I have to divide by 8 to keep it normalized. This is for the two large peaks. Oh, sorry. And for the smaller peaks, it will be 1. 1, 3, 3, 8. Fit it. I have a mistake again. Where is it?
There's J 3 times.
Here. Yes, here. And here I've copied it at the wrong place. So let's verify. I have one of the large signal with plus j over 2, large signal with minus j over 2. And to make it clearer and well aligned, I'm going to write it like this. Oops. And now I have a small signal with plus 3j over 2 and a small signal with minus 3j over 2. Let's fit it. So sometimes, so what happened here? Maybe I have to give it to make it larger at the start. A bit, a little bit more. Yeah, now it works. So you see, the initial starting point of I, for some reason, made it work at the second time. So as you see here, the quality of the fit is rather good. I've really used all the constraints I could. I have a small number of free parameters. Only the central frequency, the width, the J coupling, and the overall intensity. Because of course what I could do is if instead of doing 3 divided by 8 times I0, and I could have written I1, I2, I3, and I4. But this would create 4 free parameters instead of 1. And because I know from theory that the pattern is 1, 3, 3, 1, it makes much more sense to make it this way. So this is what we call a Lorentzian deconvolution. And now I'm going to show you how I can fit all the spectra one by one in a quite rapid manner. So I'm going to give it a name, quadruplet deconvolution. So there's a very useful feature in MATLAB that you will see here. It's generate code. It's whenever you use something, an interactive tool, you have the possibility to generate the code. And what it means is that it creates a code that does everything that I've done in the interactive window is now done in a code. So let's see how it works. So it's a function. So a function takes inputs. Here we have two inputs, and it will output some results. I've just modified slightly the way it's written because I prefer to have it like this, more aligned. So it takes W and S as input, so the X and Y variables. This prepare curve data, I don't know exactly how it works, but it modifies the data in a way that the fit will use. And here, the very important part is fit type. So it defines the function of the fit. So you see the function I've written earlier is here, and it's strangely it is a string. It's not code. It's really a string of characters. So you see the whole function is here, and these are just some options that MATLAB needs. But but I don't know exactly what it means. This we leave it as it is. And so this is important. I'm going to align it so it's clearer to read. So this was 1 to the 10, so we easy like this. So I'm going to align these numbers and explain to you what it means. So these are my fit parameters. Unfortunately, you have to remember how they are ordered, and I always forget. So it's by alphabetical order, and it starts with capital letters, and I never remember where the numbers, how they are taken into account. But here it's I0, J, G, and W0. So I'm gonna write it here. I0. Oh. What did I say? J, G, J, G, and W0. So these options define the lower boundary. This is what I define the lower boundary for the 4 parameters in the, in the interactive tool, the upper boundary, and the starting point. So if I want to modify them later on, they are here. And this part really does the fit. I did a mistake. It takes the X and Y data as input, the fit type that was defined here, and these options for the fit. And it returns the fit results and a variable that contains the confidence of the results. And then it does a plot. So we are going. I put this n here so that this is a function that I can copy in my file here. You will see why later on. So I create a section dedicated to functions. So now, when I can call this function called createFit. I'm just going to rename it, by the way. Quadruplet. So quadruplet fit. It's underlined in red because it's not used, and MATLAB is surprised that I don't use it. So what I can do is cool now is to fit all my spectra using this function one by one. And to do this, I'm going to use a for loop that takes value from 1 to n. Why 1 to n? Because I have n spectra. N was defined here. So I know that I have n spectra. And what I want to do is so I'm going to create, I have 4 parameters in my fits. So for each spectrum, I'm going to fit these 4 parameters. So I'm going to create some vectors where I can store this, these parameters. So it will be called I0s. n lines, one column. So as I told you last week, I always prefer to define my variables before I use them.
You may have already said this, but just to ask, if you define all of these variables, so basically the size of these vectors before you fit, this limits the number of iterations or controls the number of iterations of the fitting?
Doing this, you mean?
Yeah.
This is only to have control over, it's just a habit, because if I will come back. So let's do this. I comment it so that it's not active. You will see what MATLAB tells me. And I'll come back to your question in a minute. So let's do it like this. So now as input, what I have to put is this here. This will always be the same x-axis, but what will be changing is this. The y-axis will depend on the iterator. So now if I do this, it will repeat the fit n times. Just to start with, I'm going to do that from 1 to 4, because you will see that it will create a plot for each spectrum, and if I go to n, I will have 60 plots, and it will be a bit of a mess. So I just start. I will run this loop with these parameters. So what it did 4 fits, as you can see here, varying. So this is the first spectrum, second, third, fourth. And by the way, you can close all the spectra at once doing this. Here I have a warning, error updating legend. Oh yeah, it doesn't like to have this syntax here. This syntax means, for example, if I write this, it will write 0 as a subscript. So if I have nothing after the underscore, it's not happy. So I'm going to remove them. So now I do a little trick not to have to see the plots all the time. I add a condition. So it will only plot it if this variable has a value true. And I add this as an input parameter here. Plot fig. So now this doesn't work anymore because this has only 2 parameters, and I'm going to write here false. So that now if I run it again, I run it and I have seen nothing because it hasn't plotted the results. So what this loop does at the moment, it puts the results here, but every time it erases them. What I want to do now is to store the results. And the way you call the results, it's a structure. So it works like this. I've put the same name for this and this, but it doesn't need to be the same, of course. You see now, Stuart, this is underlined in red, and MATLAB is not happy because it tells me that the size of the vector will change size on every loop iteration. So whenever it goes here, MATLAB will have to resize and these vectors and allocate space for them. That's why.
That I understand, but I was just writing in the chat, but I'll say it here.
Mm-hmm.
So let me give you another example. So say you have a case where you have a spectrum which takes greater than n iterations to fit. Will the fact that you've allocated n space mean that the fit will stop before it converges?
Oh, no, this n, or what I'm defining here, is I'm making a new fit all the time. So it has nothing to do with convergence. See, here it means that I'm quadruplet fit is a function that takes x values, y values as input, and when I equals 1 is the first spectrum. When I equals 2, it's the second spectrum. And it will make the fits for all spectra. So this value is not related to the iteration, but what you say is important. So,
okay, I see, because this is a time course. This is spectra as a function of time.
yes, in a way, yes, it is.
Okay, I see what my confusion is. Okay,
But
thanks.
what I often do here, you have maximum iteration. Usually, I multiply it by 10, so that I give it more time to converge, because anyway, the function is super fast.
Okay, I think that's answered my question.
Okay, good. But I'm still going to do that. Generate code. Oh. Because the data selection is incomplete. Okay, I have a problem here. Yeah, max iteration. It's defined this way, so I'm gonna use this as well in my function here. I add this option, so that I'm sure that MATLAB tries a little longer before it stops fitting. So now this will run for all spectra and store the variables here. I'm also going to create a new one that will be called E for errors. And for, I'm not sure this will work. We will see. Let's verify the structure of, so GOF has this, there's a function conf int. Let's check how it works. This doesn't work. Just remind. This is what I wanted. I don't need GOF, in fact. So when I take fit results and I use conf int, you give me the interval of confidence of the different parameters, and I will use it later on for to plot the errors on the fits. So I've created, this is an array with n elements, with I mentioned n in the first row, and 4 by 2. I would rather write it like this, 2 by 4, so that now I can write this. So when I do this, it gives back a vector, a matrix with these 8 elements, which are, this is the lower boundary for all parameters and the upper boundary for all parameters, the interval of confidence. And it will store them here. Let's see if this syntax works. By the way, something I often do, you know, the level of where it is in the process. I will explain in a second what I'm doing. Here what I've created is a disp, just displays something here. And here I is the value of this, n is the maximum value. I turn these numbers into strings, and then I put them together. I'm gonna process here, and let's run it again. So you see now, this helps me, this just shows me the time it takes. And before I let it go to the end, I'm gonna show you the time it takes, and then I will show you a trick that makes it much faster. So let's just wait until it's completed. In the meantime, I'll already explain you the trick I'm gonna implement. Whenever it fits, it starts with some sort of random or not optimized initial parameters that are defined here. But what I can do to go much faster is to define the starting point as the results of the previous fit. So as an input here, I will create this variable start point. I'm gonna, so I will define start point. Here, explain you in a second why I do this. So here I define start point. Now this function needs to have start point as an input. And what I will do is at each iteration, I'm going to define the start point of the next one as the result of the previous one. And you will see it will be really much faster. So what does this mean? In the beginning, we have this starting point. It does the fit with this starting point. And then the variable start point takes the result of the previous fit. So in the loop, so you see, let's still wait until the end so that you can see how much time we save doing this. So tick-tock tells me the time that separates these two operations, and you will see it will be really much faster. Do you have a question on the trick that I have just done? Because this is a really important one. If it's not clear, please say it. Don't hesitate. We're almost done. Okay, so it took 157. Just to show you like an example of what, before I run the code again. So now if I plot the time and I0, it doesn't work well. We will see later on why. I think it was starting well, but then it went crazy precisely because the starting point of the fit is not right. So let's run this code again and you will see how much faster it will be. It was 157 earlier, and now it's struggling to fit because the I'm going to show you in a second why it struggles to fit. So it took 20 seconds this time. So I plot again the results. Now the results are more sensible. So this is the intensity as a function of time. And why was it struggling to fit? If you look, for example, at the 200 spectrum, this is what it looks like. So of course, when you try to fit this, it doesn't work well. So I'm gonna ask it to fit only the first 100 spectrum, because this is where I still have some signal. After some point, I don't have signal anymore, so it doesn't make sense to continue fitting. Yeah. So now what I want to do that I find interesting is to plot this result as a function of time. So I'm going to make a figure and separate it in subplots. I want one subplot per variable. This is plot 1, plot 2, plot 3, plot 4. So it's as a function of time. We had defined time earlier, but I have to take only the first n elements. I0. I repeat it for J, G, and W0. And I run this code. So this is the 4 parameters that I've fitted along time. You see the integral decreases well, in, as we could expect, mono-exponentially. Struggle to say it. But this is, I'm going to add labels so that it's clearer. X label will be time. Oops. And Y label will be I0. This is in ppm. We could convert it to hertz, but it's not better for now. This is G, also in ppm. So we can write full width at half maximum and central frequency in ppm. So you see that the value of J is more or less stable, which we can expect. This is probably just the intensity of the fit. We see that the full width at half maximum is more or less stable in the beginning, and then it starts to be crazy, but this is probably just because there's not enough signal. And you see that the position of the peak drifts a long time. And this jumps here, if I remember well, is that when we did the experiment, we hit the machine as it was recording, and it goes these sort of things. So here I've displayed my data a long time. What I can do to make it a bit nicer, I can use this error bar here. So error bar does a plot also, but you have to give it X value, Y values, and the interval of confidence along along Y. Sorry. So I want all the so I corresponds, like the first dimension corresponds to each spectrum. So I'm gonna put them all, and then if you remember, let's have a look at what E looks like if I take the first one, for example. So this is this is not what I expected. So this is the, if I put a 1 here, this is the intensity, I0. So I'm going to write it like this. I hope it will work. Oh, sorry, 1. No, this is wrong. Okay, what is the problem? It's not happy with the, I'm going to modify this slightly. Let me explain you what I'm doing. I'm going to create for each of them an individual. It will be easier like this. So I will have fit results, error. It will be much easier to handle in this way. Let's have a look if I define this here. Oops. So this is the arrow has this shape here, and oh yeah. I have a lower and upper boundary, so I have to define it this way. So it's n rows and 2 columns. So I want all the rows column 1. Oops. So this is the error that corresponds to fit parameter 2. Fit parameter 2 is J, this is G, and this is W0. Let's see if this works. Yeah, it does. So now hopefully, yes?
May I suggest that at some point soon we have a break?
Yes, I was
We've been doing an hour.
just after this this plot here.
Perfect. Wonderful. Yeah. Thank you.
Let's see if this works now. Still doesn't work. Why? So I'm going to open this. This has the shape I expected. Y negative delta must be empty or the same size as Y data. So Y data is I0. I0 has 100 here. So in this case, you type help error bar and you ask MATLAB how to write it. So what I want, yeah?
You must first put the positive errors and then the negative errors, like.
Oh yeah, you're right.
With two parameters at the end of error bar.
Yeah. So this means doing this.
Oh, negatives and positive, I guess.
Oh, yeah. Like this.
Yeah, maybe.
Oh. This is surprising. The error bar is absolutely enormous. I didn't expect it. So probably there's a mistake. Let's have a look at the.
Yeah, there's twice as much polarization as we thought there was. Good news.
So, yeah, I see. Because this is the difference. It's expressed as a difference. So it's like this. It's not very convenient the way it's defined. No, still wrong. Because this is a number larger than I0. What did I wrong? Oh. Yeah, now it's working. So you see when we plot the error bars, they are so small that we barely see them. Is it clear? I guess for me a more interesting way to plot it would have been this one. I finished with this. Instead of plotting it like this, we can have 3 lines. Hold on. I write hold on so that it plots and then it doesn't. This doesn't erase the previous one. Then I have to hold off. And I will ask it to be dot. This makes a dotted line. So when you zoom, but this is so small that we barely see it, it's the error along the along the fit.